Okay, let's take the next example. Again, we have a system of three equations, two variables. Now you may ask, what is different? What is the difference between this and the earlier one? Well, this is a hint, and I might as well steal my own thunder. These equations are those of lines which are not concurrent. They do not intersect in one single point. Rather, each pair intersects in a separate point. Okay, so what this means is we expect that there is no single solution, no one point. There is no one single solution for this system of equations, and we want to see how that plays out geometrically, vector-wise, and from an elimination perspective. Let's start. So we go to our favorite xy plane and we are going to plot these lines. X minus y is equal to 1. So when x is equal to 0, y is equal to minus 1. So x is equal to 0, y is minus 1. I got my first point here. When y is equal to 0, you will see that x is equal to 1. So when y is equal to 0, x is equal to 1. So I got my first line. Let me draw that. X minus y is equal to 1. Okay. And this is 1, 0. And this is 0 minus 1. I'll take the next one. 3x plus 2y is equal to 18. The same routine. X is equal to 0. This 0 is out. Y is equal to 9. So when x is equal to 0, I go all the way here. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 1 point. That's 0, 9. And when y is equal to 0, this 0 is out, you will see that x is equal to 6. 2, 3, 4, 5, 6. So this is the line I have. Not bad at all. Not bad at all. 3x plus 2y is equal to 18, and we have a point of intersection. So I'll tell you what that is. 1, 2, 3, 4. If you were to solve these two equations, now solving these two equations, this one and this one, we all did it in high school, you know how it is to be done. So we are really establishing some of the things we have learned in high school. Okay, this is not something new that we are learning here. We take the third line, x minus 11y is equal to 41. Okay, the same thing. This is a bit awkward. You'll see, you'll get fractional values. X equal to 0, y is equal to minus 41 by 11, which is kind of in the 3.7 range. So when x is 0, y is 1, 2, 3, 4, somewhere around here. This is the first point we got. That's 0 minus 41 by 11. Okay, let's see y is equal to 0. When y is equal to 0, x is equal to 41, and that will go a long way along the x-axis somewhere here, and hence, this, this line is going to look somewhat like this. Okay, again, if you were to solve this equation and this equation, you would come up with 8 minus 3. You can check that, right? Now the question is, this line goes all the way back here and hits this one too. And where does it hit it? It hits it at minus 3, minus 4. So it really hits this line at minus 3 and minus 4. So we got the geometric representation of these three lines. We already knew it, but it's nice to establish them and see how it looks. X minus 1 is equal to 1. 3x plus 2y is equal to 18 and x minus 11y is equal to 41. So look at the first point of intersection, that's between x minus y is equal to 1 and 3x plus 2y is equal to. Okay, that's 4, 3. Then let's look at 3x plus y is equal to 11 and x minus y. 3x plus 2y is equal to 18 and x minus 11y is equal to 41. That's right here. So that point of intersection is 8 minus 3. And then the third pair is x minus y is equal to 1 and x minus 11y. Okay, these two go on to meet here. So this point of intersection is minus 3 minus 4. Okay, that's what we got. So this is, we just did the geometric part in the xy plane. We're done with that. I want us to go on to the vector part now. So this is where the interesting interpretation from a linear algebra point of view really starts. Okay, as we did in the earlier video, I will start by writing the matrix here. 1, 3, 1, minus 1, 2, minus 11. Hold on for a minute. Yeah, I just wanted to check the video is still on. This is the third time I am trying to do this and the camera keeps failing. Okay. We already did this in the earlier video, right? Okay. Let me check my notes. X minus 11y is equal to 41. 3x plus 2y is equal to 18. And x minus y is equal to 1. Fine, we are fine. So we already did this. We verified our matrix multiplication fundamental. So what you really get is y into minus 1, 2 minus 11 is equal to 1, 18, 41. Okay. So this equation, now this is a linear combination of vector v1 and vector v2 and this is v3. The question really is, okay, can this be solved? Now, if you look at, we already know there is no one single point in which these three lines intersect, okay, which leads us to the interpretation that there cannot be values of x and y such that these can combine to give you this vector. But we need to convince ourselves about that from vector perspective. Okay, how do we do that? So we go back to a plane that we used, similar to the one we used in the earlier video. Okay, now what is this plane? This is the plane that contains the vector 1, 3, 1. It also contains the vector minus 1, 2, minus 11. Minus 1, 2, minus 11 and 1, 3, 1. Fine. Now, as we said in the earlier video, there is always a plane which contains any two vectors. Any two vectors are coplanar. So these are coplanar. The point is, if these two vectors can be linearly combined by x and y, values of x and y to give this, then it stands to reason that this vector should also lie in this plane. And looking at this, we expect to reach the conclusion that this vector does not lie in this plane and hence these two vectors cannot linearly combine to reach this vector. Let's see how we do that. So again, as earlier, I'm going to try and find the normal vector to this plane. And as we did in the earlier video, okay, we take the cross product of these two vectors. The cross product of any two vectors is the normal vector. Minus 1, 3, 1 cross minus 1, 2, minus 11. I'm going to zip through this. I'm not going to explain how a cross product is calculated. Sorry. Okay. This one. Minus 33. Minus 2. This one. Minus 1. minus of minus 11, and the third one is 2 minus of minus 3. Okay, so the normal vector came out to be minus 35. This is minus 1 plus 11, that is 10, and this is 2 plus 3, which is 5. So this is the normal vector to the plane containing these two vectors. Okay, what's the other thing we want to do? Okay, I am going to construct the equation of this plane. Okay, so this vector minus this vector gives me this vector, which really is this vector minus this vector. So minus 1, 2, minus 11, minus 1, minus 3, minus 1. I hope I got it right. Minus 1, 2, minus 3, minus, yes. So minus 2, minus 1, minus 12. Sorry, this is not really what I want to do. Okay, the way to find the equation of a plane given one point in the plane is to take a general point, general vector x, y, z. Sorry about that. Yeah. So y, z, and now to construct a vector in this plane using the subtraction of these two. So what we are really talking about is x minus of minus 1, y minus 2, and z minus of minus 11. Okay. So this vector lies plonk in this plane, sorry, this one. And if this is the normal to this plane, then the dot product should be 0. Okay. So that means x plus 1, y minus 2, z plus 11 dotted with 35, 10, 5 equal to 0. So let's calculate the dot product. I get the feeling that I am doing something wrong here. Okay, I'm going to take a quick look. 1, 3, 1, minus 1, 2, minus 11, x plus 1, y minus 2, y minus 2, z plus 11. Oh, I thought so, because I was forward calculating the dot product and expecting something. We'll come to that in a while. So what we get is, so if we calculate the dot product here, minus 35 into x plus 1 plus 10 into y minus 2 plus 5 into z plus 11 is equal to 0. Minus 35x minus 35 plus 10y minus 20 plus 5z plus 55 is equal to 0. I'll look at the constant terms. Minus 35 minus 20, that gives minus 55, and plus 55, that so that zeroes out. So we are really left with these. Minus 35x plus 10y plus 5z is equal to 0. I'm going to divide by minus 5 to simplify this. So I get 7x minus 2y plus z equal to 0. So this is the equation of this plane right here. Now the thing is, if this vector were to lie in this plane, it should satisfy the equation of this plane. So that's what I'm going to try. 7 into 1 minus 2 into 18 plus 41. This equals 7 minus 36 plus 41, which equals 29, 41 minus 29, which clearly is not equal to 0. And hence I conclude that this vector does not lie in this plane. And if we have a situation in R3 where these two vectors lie in this plane and this third vector lies outside of this plane, something like this, there is no way these two will combine to give this. So I think that's the best I can do from a vector perspective. Let's go on to the elimination. Okay, let's write up the matrix that we use for the Gaussian elimination or the Gauss-Jordan elimination. 1, minus 1, 3, 2, 1, minus 1, and the augmented matrix 1, 81, 41. Let me check because I don't want to be making any mistakes here. 1, 3, 1, minus 1, 2, minus 11, 1, 18, 41. Okay, good. So I got my first pivot the way I want it, 1, perfect. So I'm going to clear the entries in the column of the first pivot. R2 minus 3 R1 and R3 minus R1. That gives us the first row stays as is. R2 minus 3 R1. This zeroes out. This is really 2 minus 3 of minus 1, which gives me 5. And this is 18 minus 3 of 1 here. So that gives me 15. And the third one, this zeroes out, R3 minus R1. This becomes minus 11 minus of minus 1. So that's minus 10. Yep. And this is 41 minus of 1, which gives me 40. Very good. Okay, what is the next thing in the reduction that I do? I want to make this pivot, this is the second pivot, equal to 1. So I do R2 divided by 5, and that gives me the first row stays as is. The second one, this gets divided by 5 to give 1, this gets divided by 5 to give me 3. We didn't do anything out here. Okay, so I got my first pivot as 1, I got my second pivot as 1. I've already cleared entries in the column of the first pivot. Now I'm going to clear these two entries in the column of the second pivot. That's the logic applied for Gaussian elimination. So I'm going to do R1 plus R2 and R3 plus 10 of R2. Okay, so that takes me to R1 plus R2, we still end up with 1 here, minus 1 plus 1, that gives us a 0, 1 plus 3 gives us a 4, R2 stays as is, and let's look at what happens through R3. 0 minus 10 plus 10 times of 1 gives me 0, 40 plus 10 times of 3 gives me 70. Okay, so I think now I am at the reduced row echelon form. Okay, I stop here and now I start interpreting. So my interpretation starts with, as usual, the bottom row. What do I have here? Really what this is telling me is that 0x plus 0y is equal to 70. Okay. This really doesn't make sense. There is no way we are going to find ever values of x and y such that combining with them with 0 gives 70. Okay. So this is where we stop and say that we have failed, the elimination has failed, or we have an inconsistent system of 3 equations. There is no solution. We have earlier reached situations where we got 0 equal to 0, and there we said we can't really interpret this, and we went to the other 2 rows. Here we cannot do that because kind of what again it tells us. You remember the proof by contradiction thing that I said in an earlier video. We started with an assumption that this system has a solution. We started with that assumption and we came to an absurdity. And if we have come to this absurdity which cannot exist, then that means our assumption is wrong and no solution exists for the system of these 3 equations, which really means no single point of intersection. Our video can end here, but I'll point out some interesting things. Okay, So this tells us we are in an absurd situation, but look at these two. Okay. Now these two rows have progressed almost as if you can look at them as having progressed almost as if you had a system of just two linear equations, right? If you had these, then what you would really get is, if you didn't have this, x is equal to 4, y is equal to 3. And that's the solution for if this were a system of these two equations. If you were to switch rows, which you can do, and you were to have x minus 1 is equal to 1 and x minus 11y is equal to 41 as the first two rows, then I am telling you, you would reach minus 3 here and minus 4 here. And if you had these two, by the way, in this case, this would be the third equation, 3x plus 2y is equal to 18, and that would give you an absurd result in the third row. Okay? Now, if you were to have these two equations as the first two rows, 3x plus 2y is equal to 18 and x minus 11y is equal to 41, be sure that you would get 8 out here, 1 and 0 out here, and minus 3 out here, 0 and 1 here, and you would again get an absurd situation here. So, a solution exists for these two equations if you were to just consider them as a system for these two equations, but put together, there is no common point of intersection. In the vector part, we saw that these two vectors could not combine to give us this vector ever. They could not linearly combine. And these are the interpretations we come out of elimination. So I think let's end this video here. It took me 3 takes to do this video, but I'm happy I have come to this point finally. Thanks.